Hey guys, and welcome to the final part, part 3, of the 3 concepts that I feel are the most important for beginners to master in blueprints. So the first concept that we talked about was events. It was the beginning of code, the origin of our code. What events do we use and when do we use them? The second concept that we talked about was really like the lifeblood of communication inside making games, and that is actor references. It's how we communicate between blueprints. I really can't describe how important that concept really is, and understanding it and being able to just use it whenever you need it. It possibly is like the most important concept out of all of them. And the last one is, I believe, something that is just fundamental to making video games, and if you don't understand it, you will always be looking up tutorials, and that is vector math. Math is a brutal word that often scares a lot of us, but we can really simplify it, and I hope I really do a good job in this section simplifying vector math. So what I'm going to do is I'm going to show you the basic operations of vector math, and we're going to go over addition, subtraction, a little bit of division, and a little bit of multiplying. And I believe if you can just understand the basics of it, I think it's at least like a good foundation. And from there, I really implore you to look up some topics beyond that, and I'll go over that at the end of the video. So what I'm going to do to explain some of this vector math is I'm just going to drop a few things into our scene. We're just going to drop a normal cube over here, and we're just going to drop another cube over here. I'm going to open up our level blueprint. I'm going to take away some of the code that we were using before. We're just going to take away our spawning. We don't really need this stuff anymore. We're going to go over just some math. So what I'm going to do to get some actor references in our level is I'm going to select the, or actually I think, no, we'll just do the one cube at first. I can select that cube in the level, and when I right click, I can get a reference to cube 2. So that's cube 2, and then over here is cube 1. If I open back up the level, I get my reference and I can get cube 1. So what I'm going to do is I'm going to get the actor locations of these two cubes, and now we will manipulate these vectors, these yellow pins, these vectors that we get, and we will work with them. If you are not aware what a vector is, if we break the vector, we get 3 floats. That's really what a vector is. A vector is a combination of 3 values that kind of combined into being a variable. It's really what it is. Vectors can be used for a lot of things. For locations, they're useful because if we click on the cube, we can see we get an X, a Y, and a Z because we have 3 planes of movement. You can use them for colors. Vectors can be used for like RGB on colors. Really, you can use vectors for a lot of different data. For our purposes, what we really care about here is locations. So here, what we want to do to start is we will actually, we'll add these 2 vectors together. So what we're going to do is we're going to add these 2 vectors. And what we will do is we will draw a debug sphere. So let's do that. Let's draw a debug sphere. And what we're going to do is draw debug is really a way of visualizing things. So what we're going to do is we're going to draw a radius of 50. We'll make the duration really long. We'll make its thickness a little bit. And we're going to make it some really bright pink so that it's obvious. So here, just when you normally add 2 vectors together, in itself, it's not the most useful thing in the world. So we're doing this on event begin play, so when we hit play, we should get a pink circle, and it's kind of weird. It doesn't really make sense, like, where it is. And the reason being is that normally when you add 2 vectors, the reason being is that you want to use something in local space, and you want to move it to world space. So actually, I'm going to back up, and we're actually going to take one step a little different. Actually, to explain this, we are actually going to remove this code temporarily, and we're actually going to go back and use our cube actor that we used in the previous videos. So really what I just want to use this cube for is because it is a blueprint. It is an actor, and we can add some code to it. So what I'm going to do with it is we're going to remove our spinning so it doesn't spin anymore, and actually I'm going to add a vector variable, and we're going to call this vector offset. And I'm going to change it to be a vector. The vectors are yellow, and what I want to do is I want to do something a little special. I want to make it instance editable, and I want to do show 3D widget. And what this is going to do for us is that this is now going to give us this little diamond inside of here, and now we can move this vector offset. And if you look here under our default values, you can see that we have a vector offset. When I put it perfectly center inside of the cube, you can see its location is 0, 0, 0. When I move it, say 100 units Y to the side, it's negative 100 Y. Look at the location of our actual cube though. This is the actual location of our cube. This is the location of our offset. So you can see here that I named it so. This value right here, this variable that we have, this is an offset from its parent. So our cube itself, its y is 420y, but the location of our offset is negative 100y. That means that if we added them together, the y location of this offset should be 320. So if that makes sense to you, what that location is, this offset, it is technically local, or it's technically local space, or it's relative location. There's two words that you can use for this. It's relative to the cube, or it's in local space. There's two things. There's called world space and local space. The location of this cube itself is world space. This is the location in the world. The location that we have for this offset, this negative 100y, is local space or relative to that cube. So if we drew a debug sphere on event begin play inside of our actor, and say we took this offset and we did draw a debug sphere. Actually, let's go into our level blueprint. Let's just copy paste that one since we already have some of the settings set up. Just make it simple on ourselves. Let's just hook up that offset. What we don't expect to happen is we're not going to be printing the sphere at that location. So I'm getting the location of that vector offset and I'm putting a sphere in its location. When I hit play though, I think this is our actor, we don't have that sphere. The reason being is that sphere is going to be somewhere underneath the world. The reason why is that 0, 0 in the world is somewhere around like right here on my camera. That location is relative to the cube. It's not a world space location. It is a local space location. I apologize for my cat. And really what we want to do, if we wanted to print the actual world space location of this vector, is we would need to add it back into the actor location of our parent cube. So if we do that and now we print our debug sphere, you can see we actually get the location of that offset. And if I back up, the reason being is that you can see the world location of our cube is negative 600, 420, 220, and our offset is negative 100. That means our offset is negative 100 units y of our cube. So if we add our offset back into our parent, you can see it turns a local location or a relative location into a world location. So that's really what addition is useful for, or at least base addition. Normally you don't use addition too much, or I guess let me rephrase that. You don't use addition for too much else, at least very bare bones addition, for much else other than converting local space to world space, or at least I haven't encountered much of it in my few years. So there's something else that we can actually do with addition. So if we remove that and we go back over to our level, you can remember that when I added these two cubes location together, these two right here, it didn't really give us anything of value. It's just kind of a circle out in the middle of nowhere. But there's something interesting that we can do, in that if we divide this by 2, sorry, not a vector, if we divide it by a float of 2, you can see that it will actually give us something quite interesting. And if we hit play, you can see suddenly we have a location here, it will be a sphere, perfectly in between the two cubes. So addition in itself with two world space locations, two world space vectors, isn't very useful by itself. But if we take that addition and divide it by 2, you can see we get a center point between two actors. That can be quite useful. And the other thing that we used addition for over here is that we took a local location or a relative location, added it to whatever it was relative to, its parent, and that gives us the world location of that relative location. So that's addition. Pretty simple, I hope. That wasn't too complex. So let's move to subtraction. So if we subtract two actors from each other, it doesn't really give us much by itself. What it really gives us, what this represents, is a line between two actors. It's a visual for a distance between two actors. You can see that when I subtract those two actors, it doesn't really give us much purposeful. It just kind of like the addition. By itself, it's not very useful. However, what we can do with this vector is that we can get the length of it. And when we get the length of this vector, what we can actually do is we can print it. Print string, let's print it. And now if we print this, this float that it gives us, you can see it gives us 840. And actually, we're going to make this a little easier on ourselves. So let's see. Let's make this negative 1,000. And since these have the same x and the same y, what we can do is we can get an offset. So let's set that to 0, and that's 1,000. So these are 1,000 units away from each other. If you, oh, no, that's 70. So let's do that to 50. So now we're at 50x and 50x on both of them. We're at 220z and 220z. So the distance between these two actors will be the difference in y. 0, negative 1,000. So now if we run this code again, where we subtract the two actors' location against each other, get the length of that vector, that should print out 1,000. And you can see here it gives us 1,000. If we wanted to, we could make this even farther. We could take this from 0, and let's make this a positive like 200. Now it should print 1,200, and you can see here that's how it does it. So what subtraction is useful for is giving us a line between two locations. Here, what this vector represents is a magnitude, if you want to think of it that way, of a line between two locations, and that if we get the length of that line, if we get the magnitude of that line, that will give us the distance between two actors, and this is insanely useful. I do this exact piece of math to measure distance more than I can even tell you in my games. If I ever need to know how far away two things are, this personally is the piece of math that I use. It's insanely useful, subtraction. So the last one that we're really going to go over is multiplication. But to do that, we're going to go back and we're going to look at some code that I wrote back, I believe, in the second video. And that was when I pressed fire, we did a line trace. So before we get into math, I want to go back and I want to fire this code so we can see it. So here, I was doing a line trace, if you remember, to see what we hit in front of us. You can see when I click, it creates a line from where I'm standing all the way out in front of me. And we are using that to do line traces to try and get some actor references. So how did we make that line? Well, what we're going to be using is we're going to be using some addition that we just learned, and we're going to be using some multiplication. Here is kind of a special node. This forward vector, this is a normalized vector. And what a normalized vector means is that the vector has a length of 1 or has a magnitude of 1. And why that is important is that if we made a line, just like at a diagonal, at some random diagonal in the world, so that it had a weird x, a weird y, and a weird z, what would come back is if we normalized that vector and we added the x, the y, and the z together, it would equal 1. And that's important that if we have something with a magnitude of 1, when we multiply against it, that means that when I multiply 500 by a normalized vector or a vector with the length of 1, this line will now go 500 units out front of us. So really what normalization does is it helps give a direction, and that's what a forward vector is. We're seeing where am I facing, where is my actor facing, and we're turning that facing into a normalized vector with a length of 1, so that then when I multiply it by 500, what this represents is a local offset or a relative offset by 500. So then what do we do with a relative offset? Well, we have to add that back into what we're relative to give us our ending location. So like we did with the relative of our cube over here, where we had that offset, we have a relative location. Remember, this is not a location in the world. This is a normalized vector with a length of 1. If we printed the location of this vector, it would be very close to 0, 0, 0 in the world. It's a vector that has some arrangement of 3 values that equal 1. But what we can do when we multiply that by 500, we get a vector with a length of 500 pointing in the direction that we are facing. So this is relative. This is relative to where we are standing. We want to now add that back into where we are standing, and you can see here that goes into the end location of our line. So then where does our line start? Our line starts where we are standing. So you can see this line that we end up creating uses a little bit of math. It really does. So we have the actor location of ourself, and then we took our facing direction. So here, I think when we spawn, if we looked at our rotation, I believe we're pointed almost like perfectly 0. So if we went back here and we looked at our forward vector, you will see that it was 1, 0, 0. So that when I multiply that by 500, it ended up equaling 500x. So when I add 500x back into where we are standing, you can see how it ends up being like 200 positive x relative to our player. So that's, or 500x relative to our player, which ends up being like 200x world space. So that's the last piece of math. If you didn't quite understand this, I'd recommend maybe watching it again, and if I wasn't the best teacher for it, you will find vector math all over the internet. This is not something that's only used in video game design. This is used in a lot of design. So that was addition. Addition is very useful for converting local space to world space. We can also add two vectors together divide them by 2, and that gives us a center point. You can use that same type of logic to get somewhere else along between two actors, that same type of logic where you add them together and divide by some amount to get between two actors. I would probably lerp though. I don't really want to go over that. But that is also a possibility. We use subtraction to get distance. So like we did here, we subtract two vectors and then we get their vector length, and that will tell us the distance between two vectors. And then here we multiply a normalized vector by a float, and that will give us basically a vector with a length of whatever amount we're applying it in a direction that here it's normalized to 500. You'll end up, as you start to learn more about vector math, you'll normalize a lot more. You'll start to learn more about that. But then once again, we just use math to convert a local space into a world space because we want to be relative to our actor. There's a little bit more vector math than this that you will end up using. Down the road, as you get more comfortable with this math and you get more comfortable with game design, I really recommend learning dot products and cross products. They are two very useful pieces of vector math that will save you performance. It will even help you solve some more complex problems in the future. Though that can be learned down the road though, that's not more immediate. What you really need to get a grasp of is adding, subtracting, and then when use multiplication and when use division. Because if you ever watch a tutorial and someone's just pumping out math really quickly and they're not really explaining it, I really hope that at least this little bit of basis will help you understand, okay, if they're adding two vectors and that's all they're doing, they're probably converting local space to world space. If you're multiplying a vector by a float, you're almost always using a normalized vector with a length of 1 and lengthening it to a length of whatever you're multiplying it by. If you're subtracting two vectors, you're usually getting distance. That is just generally a rule of thumb. So I hope that little bit of basis helps. I really recommend, if you need some more learning, I think like Khan Academy on YouTube has a ton of vector math if you want to learn it there. It's everywhere. But I really think vector math, if you're doing any type of level design or actors or locations, you have to at least understand bare bones vectors. So that's it for this series. We talked about the three most important things I believe for beginners to learn. The first one was events. The second one was how you use actor references and what they're useful for. And the third one is vector math. I think with the understanding of these three things, you can make the basics of basically any type of game. I really think those three things are really the core of making games. Beyond that, I believe you start to get into more tricky areas, and really a lot of stuff from there, it takes just time to learn. There's a lot of tricky things with collision or with types of actors, with pawns versus characters, stuff like that. I think that comes with time, that comes with understanding, but I do believe these things, if you can understand it really before you start to really dive into tutorials, I think the tutorials will start to pay off a lot more for you. So that's the series. From here, I plan on doing a bunch of tutorials for different types of games, so if you have any suggestions, if you have any questions, please let me know and I will be glad to make a video on it or answer your question. So, thank you guys for tuning in, and we'll see you guys in the next video.